work for the global research and analysis team at Kaspersky Lab. I started working there in 2009 and in Poland, and now I'm based in UK. I enjoy reverse engineering. I enjoy playing with malware, messing up with Linux, and I also enjoy playing Baldur's Gate, which I mention here on purpose. It's not like it's my Facebook page or something. In my abstract, I stated that rootkits are currently on decline, and I heard some people were saying that it's a bold statement, so I prepared some statistics. The statistics are based on our KSN system, which is Kaspersky Security Network, and this is the detection rate per day per most known rootkit families for 32 bits. So we can see that there is a slow decrease in the detection of 33-bit rootkits. And also for 64-bit rootkits, we can see that there was some decrease. These are the statistics from the period of 1 year. And those statistics include all the 64-bit rootkit families that we detect. So my claims are not without any proofs. And why is it happening? I think current times are really tough times for rootkits because 64-bit operating systems have much better security against malware that is running in the kernel space. So the kernel space is basically no longer safe for malware to run and to hide in. Also, bootkits are not a very good solution for cyber criminals because the changes made to the boot record are easily detected by current antivirus solutions. There were some ideas of hypervisor level rootkits, like virtualization rootkits. The ideas were very nice, very clever, but unfortunately, or maybe fortunately for us, they didn't got adopted in widespread malware. So the ideas are back into 2005, 2006, and we have year 2014, and we didn't see any single malware, widespread malware in the wild malware that would use those techniques. It's probably because the complexity of implementation of such techniques is too big for cyber criminals to actually implement it, spend resources on implementing it. And all those reasons forced a certain shift in the malware strategy. For now, I would say that malware goal is not to hide from the administrator, but more to evade, more to go around the detection system. So yeah, 2-3 years ago, the goal of the malware was to hide as well as possible, so nobody can see the malware, and the malware can persistently work on the system. Now, it's more about bypassing the detection. Also, another goal is to protect the CNC infrastructure, which means to keep the CNC addresses, IP addresses secret, and to allow CNC servers to run as long as possible before they will get disabled, taken over. Also, the other goal is to protect the payload. So the payload usually is downloaded at the very end. So we have layers of loaders and downloaders and a subsequent executable file that download other files that download other files, and at the end, at the bottom, we have the actual payload, which is usually encrypted, obfuscated, and it's not easy to get it. I will talk about 5 most interesting cases of malware I came across last several months. And the first case I would like to describe is a Trojan called Baldur. It catched my attention because there was an email on II mailing list. People were asking about this Trojan, and it catched my attention First, because of the name, as I was a Baldur's Gate player 15 years ago, I was really, really much into that. And the second thing was that people were mentioning anti-sandboxing techniques that are used in this malware. So I thought, okay, if this malware proves worthy to include it in my presentation, I will buy an iPad and play Baldur's Gate again on iPad. And well, let's say this malware wasn't very exciting, wasn't very interesting, wasn't the thing I was expecting, but anyway, it's a textbook example, so I wanted to include it in this presentation because it uses most of the classical, simple anti-virtual machine and anti-debugging checks. And also I wanted to buy an iPad and play Baldur's Gate, obviously. So that's why it made into my presentation. So first checks are really simple. It's the check of is debugger with the use of the isDebugger present API and the check remote debugger present, and the other check based on the tick count. And what is interesting here, the malware writers made a mistake where we have JGE instruction, jump if greater or equal. It should be jump if less, because it checks the tick count between two instructions, and for malware for the execution in the normal environment without a sandbox or without a virtual machine or without a debugger, the result should be less than this value which is stated there, the 1C2. I don't remember the decimal value of it. Anyway, it jumps to other checks, so it passes this check if the value is greater than that. So it passes the check only if it's run in the sandbox or in the VM or in the debugger. So yeah, that's pretty lame bug. Then we have some checks for windows that are opened in the system and the window names like Oli Debugger, like Autoruns. Also, we have some checks for windows with the names like GDK window top level, which is a default name for GTK applications. And I was Googling about that because I'm not sure which application is targeted by the malware here, but I would say maybe it's a WinSpy, which is a like commercial spyware product, which is written in GTK, and it uses this window name. Another one is also some default name. And also I was trying to figure out which application may it target. And what I found on Google, it's that Malwarebytes anti-malware solution use this name for a window as well. Also we have checks for the username. And the maltest is the username which is used by Avast Sandbox. And there is some strange username, which is Tequila Boom Boom. I have no idea what is that, which sandbox or honeypot or application uses that, but I was able to track this user to use the IP in France. I think it's some honeypot setup on a French server, or something like that. Also, we have other checks, like the check for the name of the physical drive in the registry. And this is something very classical. Those checks are done by by most of the malware. Those are checks for VirtualBox, for QEMU, and for VMware. What is interesting here is the check for the API called the wine-get Unix file name, and obviously it's the API that is included in Wine DLL, Wine kernel 32 version of kernel 32 DLL Wine version. There is other interesting check, which is the check of the size of the hard drive. And if the hard drive is less than some specified value, it's probably being run in the sandbox or virtual machine. If the malware detects that something is wrong, that it's run in sandbox or that is being monitored, it does the crash, but it's like you can't see on the first glimpse that this code would crash the operating system. Why it happens? It's just because that there is no stack adjustment before return. So the address, the return address, the value of the return address on the stack is invalid. So it will return to some non-readable address and it will crash. A second example, this one actually I liked very much because it's a multi-staged exploit which drops a very nicely protected binary, which was a spyware, some generic spyware. The main payload was not very interesting, but what was interesting about this sample was exactly the exploit, which used a lot of anti-heuristic techniques, and the loader of the binary, which was also using a lot of anti-sandboxing and anti-VM checks. I wrote an article about the exploit itself, this version of this exploit. So if you are interested in more details about the exploit, you can go to the secure list and try to find this article. So the shellcode had 4 stages, which is not really very common. It had the ROP chain, it had the decryptor stage, the egg hunter stage, and finally the final stage of the shellcode was the dropper of the malware. Here we can see that it was consisting of multiple OLE objects, which was used as an anti-heuristic technique. Also, there is some obfuscation. We can see that there is a list view class ID, which is used by this kind of exploits for CV0158. But it's obfuscated with brackets, so heuristics engines can't rely on the signature anymore in this case. Also, other constants that this exploit uses are obfuscated in the same way. And the size that triggers the exploit is also obfuscated. We have the first part of the code is ROP shellcode. So we can see it uses a DLL that is loaded to the memory at the address 27 blah blah blah. Which actually I just found one version of this DLL. It's MSOCTLX library. But I checked 10 or 15 versions, and only one was compatible with this exploit. So I don't know, maybe they didn't include the other libraries. Anyway, then after the ROP, there is a decryptor part, which starts with FSTNV instruction, which is D9EE, and it uses this instruction to obtain EIP, instruction pointer, which is also something really rare. It's old technique, but it's rarely used in contemporary exploits. This is the egg hunter part. It goes through the memory and looks for a signature, and it uses the isbat read PTR function to check if the memory is readable or not. Once it finds the signature, it decrypts the code which comes after the signature, and the code is the MZ file, and after the MZ file, the stage 4 of the shellcode. And after the decryption, it proceeds to the 4th stage of the shellcode. And the 4th stage, what is interesting about the 4th stage is that it uses COM objects to run the binary. So it's also not very common technique, and I'm not sure why is it used. Is it some anti-heuristic trick or something, but yeah, it's the first time I saw something like that in the shell code. The payload it decrypts the loader, and yeah, the first, the only function actually in the that is not encrypted in the download.mz is the main function, which has a decryption routine, and the decryption routine is interesting because it computes the XOR key, the key for decryption, based on the system time, on the year got from the system time. So depending on the year that is set on the computer, the key is different. And it will be decrypted properly only for the year 2013. So it's a binary which lives only for 1 year. Actually, not even, because there is another check for a month, and if the month is equal to December, there are some calculations, and finally the code will crash. So the expiry date of this binary is end of November 2013. After that date, it will not run properly. Yep. Then, after the decryption, this malware has a lot of checks, the simple anti-debugger and anti-VM checks, that like the ones I showed you in the previous example. So I didn't include them here. But what is interesting again, there is a kind of backdoor which allows probably the developer to skip all the checks to debug the binary or something, and it computes the hash based on the computer name, and if the hash is equal to 20 C7 blah blah, it just skips all the check and goes to the next part. It also sets before the checks, it sets the SEH routine. And obviously it's a malicious function, so it will trigger the exception later to execute the SEH routine. Yeah, after all checks, or if in case of the backdoor, it goes to this code here. And like I said, it tries to trigger access violation by trying to write into non-readable memory. And if there is no exception, it means that something is wrong, because on the normal system there would be an exception. So if something is wrong, or if any of those checks before failed, it goes to the dummy code. And what is the dummy code? The dummy code is just a backdoor code which is really simple and small and doesn't do nothing. So it's just basically open the ports, listen on it, and that's all. So if any sandbox VM is detected, it just opens this backdoor and do nothing. If everything goes okay according to the malware, there should be exception triggered, and the SEH routine should be executed. So inside the SEH routine, first the malware checks the exception code, which has to be equal to exception access violation. If it's not, it just returns, exits. Then it confirms the exception address, which has to be equal to the address that malware sets, that the exception occurred. And yes, again, if it's not correct, it just exits. And after that, it writes some arguments to the stack using context record, and overwrite EIP in the context record with the pointer to the next function. So after that, it just will run the decrypt run code function with the arguments next say decrypt function, the next argument encrypted dropper code, and the next argument 40 age. Then it proceeds to resolve APIs. And what is interesting about this thing here is that it uses some kind of anti-hook, anti-breakpoint technique, in which it copies the first instruction from the API, and after this first instruction, it copies jump to the address of the API +2. To understand it better, you can see it here. It goes after it resolves each API. It copies the first instruction. And then copies the first instruction to the buffer, like for example, move EDI, and then it jumps then it copies a jump instruction, followed by the address of API minus this function. So in the memory, it looks like that. There is an array of, I call it code snippets, but we can call it trampoline as well. Which consist of the first instruction of the API, then the jump to the API. And if there is some breakpoint put on the API, like on the first, it's usually put on the first instruction of the API. So if during the execution of the code someone will put breakpoint on the API, malware will not see this breakpoint because it will use this trampoline to get to the API, not the API call itself. So it will skip the first instruction, which would be overwritten by the breakpoint. And this sample is for recreate key XA, so you can see that there is a move EDI, jump, recreate key XA +02. After that, malware creates a MSI exec process, and it creates it in the suspended state, and then it overwrites the entry point of this process with a push and the address of the next stage function and return. So after resuming this process, it will effectively go to the next stage decrypt function. What is interesting about the main payload, there is only one thing interesting about it, because the main payload here was a simple bot that responded to a few commands like push file from the server, download something, blah, 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 but it's really nothing exciting. What is interesting is that it uses the APC procedure to decrypt the URLs of CNC servers. I don't know why, actually, but it's the first time I see something like that in malware, so I thought maybe it's worth mentioning. Another case of password stealer, which was also delivered with actually the same exploit, a little bit different. The obfuscation technique was a little bit different, but besides that, it was the same thing. And it uses SEH in a different manner. It's in the win main function, there is only this code, there is nothing else. It's just like it sets the SEH and then it triggers the exception. So basically it uses the SEH chain to execute code blocks. So here, when the division by 0 exception will be triggered, the control will pass to the exception handler, which this is the exception record. We can see that the exception record contains two functions that handle the exception, but the first function that will be executed is the handler 11, which again just triggers the exception. After this second exception, the handler 12 will be executed, and this is the handler 12, which contains anti-sandboxing, anti-emulator technique, which I call dormant phase. It's just a loop of doing nothing, sleeping, doing nothing, sleeping, doing nothing. which aims to overrun the sandbox or emulator, because usually there is some specified time frame in which the sample is run. So on my computer was like 10 or 15 minutes this dormant phase, so I think it would overrun pretty much all of the most popular sandboxes and emulators. Then it decrypts the rest of the code, the next phase of the code, and then it sets the exception handler number 2 and triggers the exception, and so on. In the exception number 3, it checks if the trend micro product is installed. It does that by checking the registry key and the path of the binary, trend micro binary. If there is no trend micro, it will inject to SVC host, but if it finds trend micro, it would prefer to inject to antivirus, to trend micro antivirus product. So and then it sets a second exception handler, fourth actually, and triggers the exception as before by doing division by 0. Here this is the exception record for the exception number 4. And we have 4 functions, but the first function executed will be handler 44, which creates a process, either trend microprocess or SVC host process, suspended obviously, and it will try to overwrite this process with a malicious code. It also decrypts the main payload into the binary, so it decrypts the payload and saves it as a binary value in the registry in the key just HKLM or HKCU software, and the value name is rar. The next case is about Zeus, and well, I was monitoring Zeus for a couple of months. I was collecting the samples and checking them for anti-debugging techniques. And actually one of the samples was quite interesting because it used a Windows messaging system in order to avoid emulation and sandboxing, especially if the sandbox doesn't have implemented all the doesn't emulate all the GUI mechanisms, and it also used SEH in another manner. And what was also interesting about this one, this sample, was that there were really multiple downloaders. It's like Russian dolls, one inside the other. So each downloader was similar, used similar anti techniques, and each one was pointing to another one and another one and another one and another one and so on. So it was a little bit funny. So first of all, it uses the function load cursor to execute the malicious routine, anti-debug and prepare. And this routine, it uses Windows messages, so malware sends the messages to Windows messages to itself. And after receiving the messages, it triggers a specific function. So first message it sends is get min max info. And after sending this message, after receiving this message, it triggers the anti-debug trick. Then it sends the WM NC create message, which triggers checking the debugger function. Then it sends NC calc size blah blah, which triggers the function that resolves APIs. And at the end, WM create, which will trigger allocating the buffer in the memory for the decrypted code. SEH anti-debug, it sets also the SEH handler, and it also checks the return address from the create window functions as another anti-debugging trick. So if the address is not the one that malware expects, it will exit the process. Otherwise, it will just return and the execution will continue. The anti-debug technique is a little bit obfuscated with the crazy numbers, but what it does is reading and writing into the exception record. So it checks the exception address in the context record. It checks the exception address, and then it writes the exception address to the SEI. Not register, SEI in the to the context record at where the SEI is stored. And after coming back from the handler routine, it will check the ESI register, and if it's not the one that was set inside the handler routine, it will exit. And then it will run the enum Windows function to trigger the callback function that will decrypt and run the downloader. And the downloader was not really interesting, but it was just like a piece of code which was designed to download one binary from specified address, and this address was not accessible anymore, so it was something short-lived, which also becomes a paradigm in the contemporary malware, to use just malware that will do its work and will disappear, so it's untrackable. Then I stumbled upon even more hardened Zeus sample, which was designed for Windows 7, and the anti-emulation technique that it used was based on the default values of the CPU registers at the entry point. Also, this one is interesting because it drops a Necrus rootkit, which is slightly against my claims that rootkits are on decline, because in case of Necrus, the statistics are quite different, but it's just one example out of many more which are declining. So the code is really obfuscated with a lot of dead code which never gets executed, but looks valid, looks legitimate. We have a lot of steps, so from one step we call another step, and so on and so on and so on. Also, there are some functions, GUI functions used, or library functions used in the code which are completely meaningless. So they are here just to confuse. And finally, at the seventh step, we have this anti-emulation technique I mentioned. It just checks the register, the default values of the EDI and EDX registers. And those values are different for Windows XP, different for Windows 7. They are different for virtual machines. They are also different for other, like for Windows XP with the Service Pack 3 or Windows XP without any Service Pack. So they kind of differ. And based on this value, it calculates another value, and it checks if this value if this value results in having like the least significant byte set or not. And based on this information, it can say if it's run inside Windows 7 or not. So if it's not run inside Windows 7, it will exit. And the check is done exactly here. So it continued then to step 8, and then to step 9, and then to step blah, 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 up until step 17, at which point it will call the main function. So that were the samples I wanted to show you. Now, a quick summary. I already mentioned what are the current goals of malware writers of malware. So the first one and the most obvious one is bypassing the detection. What they are using for that is anti-emulation and anti-heuristic techniques. Other goal is protecting CNC infrastructure. So we have multiple downloaders. We have also water-hold websites, which are the legitimate web servers that got hacked, and the malware is served there. Usually they are very short-lived, like the samples are existing on a specified website only for 2 or 3 days. And other goal, which is protect the payload, and we have anti-reversing techniques, anti-debugging, anti-VM, and lots of encryption and obfuscation, etc. About the architecture of contemporary malware, it usually comes as a loader. The first binary is a loader, which is really heavily armed with packers, with encryption, with anti-debugging, anti-VM, anti techniques, and it's used to inject and execute the dropper code. The dropper code usually is also encrypted and also consists of many stages of encryption and anti-debugging. Then it decrypts and executes the downloader or the bot code. Then the bot code is usually small and simple, and it's written like shellcode, so it's really straightforward. It also sometimes uses some anti-techniques, and it's used just to decrypt, to get, decrypt, and run the payload. So usually the bot consists, either the bot consists of a set of commands, like 5 or 6 commands just to download, write the file, overwrite, delete, something like that. Or there is just a downloader which will download the payload from specified hard-coded website and execute it. And payload, well, it's interesting about the payload that it's not really easy to get to the actual payload right now, because, well, in this, when we have a bot which just wait for a CNC to push the payload, we can wait and wait and wait and wait and never get the payload, actually, because cyber criminals might not be interested in infecting our computer. And also payload is never stored on the disk, so it's just like downloaded on each reboot or pushed by CNC and stored in the memory. It's very short-lived usually, and it's fully controlled by CNC servers. So, like I said, sometimes it's not that easy to get to the payload after doing all the decryption and the obfuscation. This is the summary of the techniques I mentioned. So we have time or condition-based triggers, which can be, the code can be triggered by only in specified time frames, or can be encrypted, decrypted properly only if specified settings are found or specified events are triggered. We have a lot of environmental checks, like checks for files on the disk, like checks for strings in the registry, mutexes, or window names. We have something new. I haven't seen it before, the check of the initial values that are stored in CPU registers at the entry point. We can call it a fingerprinting the operating system. And we have overrunning sandbox and emulators. So also often there are used instructions that are significantly slower inside virtual machines and sandboxes, like instructions like MMX or FPO instructions, or get tick count, or other instructions that might take more time inside the VM. We have benign code, which is code that looks legitimately, does legitimate system calls. And we have also something that last line called Stalin code. So here, kudos to last line for the name. which is the code that doesn't use any syscalls. So basically, if the sandbox doesn't emulate every instruction, it just sets hooks on syscalls and see only the syscalls, it won't actually see this kind of code. We have also using Windows messaging, which is also something new for me, and APC procedures. So those samples were the first samples I saw these techniques used. And we have use of chained exception handling mechanisms, which were used in a pretty different, which is being used in pretty different manners. So yeah. What can we do about it? Well, we should harden our sandboxes. We should harden our emulators. We should first thing we should do is we should get rid of all artifacts or all the traces that can tell the malware that is run in the emulator. So the strings, the registry values, the names, and so on and so on. Full emulation, so we should trace all instructions, not only the system calls. Full exploration of code, which means that we should follow multiple execution paths, not only the main execution path which is taken, but we should emulate also the other possibilities. And also we should get rid of the dormant code. We should skip the stalling loops and sleep loops and detect and skip the passive code. So that would be all. Thank you.